Good morning. Thank you for joining us for our latest Department of Defense Information Analysis Center webinar covering a DARPA program titled Agnostic Compact Demilitarization of Chemical Agents. My name is Steve Rutherford, and I'm the director of the HDIAC, and today we have the privilege of hosting Mr. Daryl Johnston for this presentation. I need to kick this off by thanking all of y'all for joining us today and saying that I'm grateful to each of you who've taken time out to join us during these challenging times. I'd also like to thank our sponsor, the Defense Technical Information Center. The DTIC mission is to collect, synthesize, produce, and disseminate scientific and technical information to the DoD and federal government users. So if you haven't taken a look at DTIC's website or checked it out, it's at www.discoverdtic.mil. You should take a moment to review those expansive services they offer. And without their sponsorship, this webinar series just wouldn't be possible. A few admin notes as we kick off. Please note that all your attendee lines have been muted. So if you got questions during the webinar, we ask that you submit them using the chat box that you can see on the left-hand side of the screen. And we're going to work to save the last 10 minutes or so of today's presentation to review those questions and discuss them. Please also note that this webinar is being recorded, and a link for that recording as well as the slides will be available at the HDIAC website for later download. So with that, it's my pleasure to introduce y'all to today's presenter, Mr. Daryl Johnston. Mr. Johnston manages the Pharmaceutical Program and Pilot Plant Operations section of the Southwest Research Institute. If you didn't know, the Southwest Research Institute is one of the oldest and largest independent, nonprofit applied research and development organizations in the United States. And Daryl oversees the operation of a pilot plant facility compliant with current good manufacturing practices, good laboratory practice, and Drug Enforcement Agency controlled substances as needed. Projects have included treatment or preventive drugs for cancer, heart attack, COVID-19, poisoning from opioids, organophosphates, as well as cyanide. Mr. Johnston's chemical demilitarization experience includes construction, systemization, startup, operations, and closure phases of chemical warfare agent demil at places such as the Johnston Atoll Chemical Agent Destruction System, Umatilla Chemical Agent Disposal Facility, Pine Bluff Chemical Agent Disposal Facility, and Newport Chemical Agent Disposal Facility. Mr. Johnston was also the Southwest Research Institute Project Manager for the Defense Advanced Research Projects Agency's Agnostic Compact Demilitarization of the Chemicals Project, which he will be discussing with all of us today. Mr. Johnston has a long history of service to the United States, and his direct support of demilitarization laboratory ops has spanned 17 years from 1990 to 2008. So you can see it's our distinct honor to host him today. And with that, I'm going to turn it over to you, Daryl.
Thank you very much, Steve. The topic, as Steve mentioned, is ACDC, the Agnostic Compact Demilitarization of Chemical Agents. I certainly appreciate the IAC for selecting this program for this forum. So what I wanted to go through is kind of a series of the histories that allowed this program to converge together. It has an interesting weave of history in it. Let me hit this slide here. There we go. Okay. First of all, let me express, of course, my thanks to DARPA, specifically Dr. Ann Fisher, not only for the funding, but the guidance and insight that she gave me along the way. Also, a great deal of thanks to the Combat Capabilities Development Command, CCDC, for their support, not only for their support in this program, which they did a tremendous job, very professional organization to work with, but also I'll show in a upcoming slide that their work on the Cape Ray project actually inspired the ACDC program. So for Genesis, I certainly am thankful for that too. I'm a contractor, so the project is DARPA funded, but certainly all opinions that are expressed here today are my own and not that of DARPA, CCDC, or the U.S. government. And lastly, I numbered almost all my slides. There are 31 of them if you guys want to keep pace with how I'm doing. All right, so as Steve mentioned, Southwest Research Institute, we've had a long history in chem demil, also in chemical surety work. We have a surety lab here at San Antonio. We've done agent defeat work, neutralization testing, and we're doing ongoing chemical weapon work to this day. I joined Southwest Research Institute in 1990, and you can see Johnston Island was already up and running, or at least they were going through their systemization. I went there in 1990. And in my first year on Johnston Island, I attended a course called Plant Systems Description, PSD training. And in that, they taught that the liquid incinerator heats up on fuel and then switches over to agent as fuel. So I was introduced to the fact or the concept that agent has fuel-like properties. Later that same year, actually probably within a week of that class, week of learning that, I'm sitting at a picnic table at the barracks, and I'm looking at the generators that provide power to the whole island and the plant. And I thought to myself, why don't we just cut out the middleman, just put the chemical warfare agent in the fuel tank, it has fuel-like properties, and burn it right there in the diesel engine. So me and my buddies all had a good laugh at that, and I got to do it years later with DARPA, and I certainly appreciate that opportunity. The other sites, so I've got the Johnston Island site, Umatilla Chemical Agent Disposal System, Pine Bluff, and Newport, Indiana. So I had the pleasure or the privilege of being laboratory manager at 3 of those sites, and then oversaw the closure of all of them, at least from a laboratory perspective. So some more background for Southwest Research Institute. We have a long history in automotive research and rapid prototyping. And highlighted here is an engine that's particularly relevant because it's what enabled us to look at an engine as a means of destroying chemical warfare agent and convince ourselves that we could not only bid and win it, but it would work. The interesting part of that is ultimately we did try this dedicated exhaust gas recirculation engine approach, but we moved away from it in favor of a modern normal diesel engine. Another piece of history that is rich for this ACDC program is the genesis of the idea. In 2014, Syria declared their CWA stockpile, and the U.S. and CCDC in particular adapted what they had as a proven technology, the Field Deployable Hydraulic System, the FDSHS. There we go. Got to get it right. But it was a new, they'd never had it on a ship before. There were a lot of huge technical and logistical challenges, and they were successful. It was a huge success. They destroyed 600 tons of chemical warfare agent, the precursor to sarin, as well as sulfur mustard, and certainly the group should be very proud of themselves. Having worked on Johnston Island and having the history that I have, I really wish I was able to be part of that, but I'm very proud of them for what they did for our country. There were significant logistical challenges in this effort. The weapons had to be secured, transported. Everybody had to deal, or the international community had to deal with NIMBY, not in my backyard. And ultimately had to be destroyed in international waters. And they destroyed, the 600 tons of chemical weapons became 6,000 tons of waste. And that's not a poke at anybody. That's just the way things are. DARPA, in particular, Dr. Tyler McQuade, the first PM that initiated this, saw this program as a huge success. And he was inspired to address it in 3 ways. He wanted to push the demilitarization all the way out to the site where the weapons are found. He wanted to minimize the logistical tail and eliminate the waste. So he briefed a proposers conference. So this is his proposer conference slide. And he wanted to use the chemistry that's inherent in soils. Not something a lot of people think about. There is a lot of chemistry in soil. And this was his presentation. He had these chemicals that could be destroyed in an environment that included a lot of energy and soil. And I keyed in on the energy part, and then that made me think about the idea that I had some 20 some odd years earlier out on Johnston Island. And I had a colleague here at Southwest Research Institute, Dr. Jamil Irwin, who recognized that combustion of many of these compounds would produce acid gases. And that soil, coincidentally, he did his PhD thesis on adsorption of acid gases on calcium carbonate. So he recognized that soil could be used to absorb these acid gases. So then we had an idea. We could bring Dr. McQuade's equation here to life, we could use the engine to destroy the chemical warfare agent and soil to scrub the acid gases. So we had to do a little bit of work on the front end to say, does this idea really work? So we got with our engine folks, and the question was, how hot does an internal combustion engine get in the cylinder? And the engine folks provided me this trace. It's a 360-degree rotation where you see it going from minus 180 to a positive 180. And this is on the combustion cycle. Not shown is the exhaust cycle, which would be another rotation of the engine. So that's how the upper right gets down to the lower left as far as temperatures go. But with the temperatures plotted, you guys can see that it gets up to 2,500 K. That's 2,225 degrees C or 4,040 degrees F. So it gets really hot in there. The next thing we had to do was figure out how much chemical warfare agent could be destroyed in that really brief cycle that it's up there being compressed. And we have the thermal decomposition rates for chemical warfare agents, at least GBVX and HD. Compliments of another Dr. Matthew Blaze here at Southwest Research Institute did that research. And so we did the math for how many half-lives would it take. Decomposition rates calculate out half-lives. So then we had to do the math for how many half-lives would we get or would we need. So to get to the goal of 99.9999% destruction, we only needed 20 half-lives. So that was good news. And then we got with the engine folks and said, given consideration of engine speed, volume, air-to-fuel ratio, heat, all those things, how long are we up there? How much fuel do we burn, and so forth? So we calculated about another that little bit of red bar when it's up there above 2,000 K. It is about 10,000 half-lives. So we only need 20. We got 10,000. So the idea looked like, hey, this will work. There should be no problem destroying it in an internal combustion engine. And then the last was to weave together the soil side of it. And we wanted to scrub acid gases of hydrofluoric HF, hydrochloric HCl, the P2O5, which turns into phosphoric and phosphorus acids, as well as polyphosphoric acid. And then SO2, which converts to sulfurous and sulfuric acid. So we wanted to be able to absorb those. The oxides of nitrogen was a different story. We knew that we could not absorb those and proposed that to DARPA, saying that's probably not going to stick. DARPA was okay with that, and we moved forward. There was an interesting chemistry. All the oxides of nitrogens going through soil did turn into NO, nitrous oxide, or the singular oxide of nitrogen. That was interesting. We didn't pursue it as a research topic, but it would be an interesting one to chase down. You guys have already seen this slide. I'm just going to run you through just a brief chronology to take you through the whole project length, and then I'll circle back to each of the topics. So in December of 2014, DARPA sent out the announcement, and it was to deal with a Syria-sized stockpile. This was the model of what we had in mind to go back to them with, to say, okay, well, they gave us the limitation of working within a 40-foot connex. So we looked at having basically a semi-tractor trailer rig arrangement with a glove box on the back end where we would access chemical warfare agent, pump that to the engines. There would obviously be a holding tank in there, and then have the engine exhaust go through one at a time. One or the other, a swing bed, fluidized bed reactor with soil in it, and then that exhaust would go out through a bag house, and then be collected outside of the vehicle. And then the engine exhaust would leave just like a normal car exhaust out a small stack with all the soil fines as well as acids and everything else removed. So it would just come out as CO2 and water for the most part. So where's my clicker? There we go. So then we got the award. So I was thankful for that. We managed to do the build an engine on a test stand, make it operational. This is a gasoline engine. We did, and it was with this dedicated exhaust gas recirculation, which is what the little sketch is over there on the side. The engine exhaust of one cylinder is used. The exhaust from the one cylinder is just burning fuel, regular fuel, and then it circulates around and is on the intake of the other. So that adds hydrogen and carbon monoxide to the intake, accelerates the flame front, so it makes the burn a little more fast and widespread inside of the engine. So we have it set up here with a fluidized bed of soil. That's the thing wrapped in white insulation there. We've got a packed bed scrubber, even a little bit more in front of the picture in that same frame. And we succeeded at month 6 with this greater than 99.99% destruction of the Simulant and 99% acid gas removal. And this was the month 21 milestone. So DARPA was extremely happy. We were very proud. So this looked like a excellent program or excellent way of attacking the problem. Then we had an opportunity to, advance the TRL, the technical readiness level, and it came up in about the March or May timeframe of 2016. And we went off and built a system that has a much larger fluidized bed reactor, packed bed scrubber system, and did some work with it. It's kind of a sideline. It took us back to the main project, so it wasn't too much of a sideline. And we concluded in the route there that we needed a diesel engine instead of a gasoline engine. I'll talk a little bit more on that in a minute. And then we discovered, that something we didn't think of was this, that the organophosphate nerve agents, the ones that have phosphate in them, produce a very viscous polyphosphoric acid when the P2O5, which is a particulate, interacts with water that's already in the exhaust. So from that standpoint, we found out some very useful information that designing a system, we have to account for this honey-like, very acidic solution that would be produced. So all the rest of it in one bite. So we, in the November of 17 timeframe, the end goal was revised from a Syria-sized stockpile to a smaller cache size stockpile. And they wanted a get in and get out scenario. So we worked out which vehicle to use, began modifying the engine and building the scrubber. Tested the system first on a test stand in April, then in the actual vehicle all the way up through October and into November. And then packed it up in December and went out to CCDC, shipped it up there, and then January and February of this year did testing at CCDC in Maryland and demonstrated 99.9988 to 99.9995% destruction and removal efficiency of an HD Simulant and 99.94% removal of acid gas. And then just to address the elephant in the room is that truck looks pixelated or blurred. So I've obscured the vehicle throughout the deck, partially because Southwest Research Institute is fiercely independent and we don't want to plug a particular vehicle type, and also because I was asked to. So I'll leave it at that. So the vehicle is blurred for the rest of the program. Slide 15, there we go. So we had to prove the concept of the diesel engine after we found some issues with the gasoline. So the gasoline engine, we found that the feed rate was limited by engine knock, and knock is high pressure spikes that are damaging to gasoline engines. There's a lot of complexity to it, but they're like explosions that are happening inside of the cylinders. And you guys can probably remember anti-knock or low knock gasolines and everything before the engine technology got to the current date. So those of you that are a little bit older, probably even had leaded and unleaded gasoline. So it was a big deal for in a gasoline engine to reduce knock. So what we found out was we could not scale up a gasoline engine, at least not to meet the Syria size stockpile. So that it was limited. But we knew that a diesel engine was not limited by knock. And so we ran a proof of concept test on this one cylinder, 435 cc generator. And without any optimization, it produced 99.5% destruction and removal efficiency. The diesel engines work on auto ignition, and auto ignition is what knock is. So knock is auto ignition, and that in a diesel engine that becomes, instead of a hindrance, that becomes a feature. So the switch to the diesel engine was necessary, and it proved out to be very useful, and it gave us a useful rule of thumb. Probably the best thing that came out of this small test was we had this feed rate rule of thumb that 10 liters per hour per liter of engine displacement. So now if somebody had a mission and a duration, a mission size and a duration, then you would want to match that with an engine that's big enough to get through the mission size in the time scale that they want. So you'd be able to scale this appropriately. So once we knew this, then we got with potential end users in the February of 2018 timeframe, and we had to come up with some specifications. The end users brought those, so we had fundamental specifications. We took those specifications, and Southwest Research Institute did a trade space analysis fitting engine size and complexity, ways of dissipating the power output, scrubber options, and vehicle load size and load weight limitations. So those were all multivariable issues that had to all be massaged to come up with what is the best vehicle to prove this out on. And this table shows part of that trade space analysis, where we narrowed it down: the vehicle, the engine size and sophistication, scrubber options, and then the one that's got the green lines. Everything turned up green, at least that was usable. Turned out to be this 4.5 liter V8 diesel engine with electronic fuel injection, superchargers to dissipate the engine power output, and I'll talk more on that later. Ammonia rather than soil to scrub the acid gases. So that's a big switch, and I'll talk more on switching to ammonia. And then a pickup truck configuration. So we can put the scrubber in the bed of the truck. It just made the design significantly easier than let's say an SUV or one of the other military type vehicles. So we had to come up with switching from soil to ultralight scrubber in order to get a get in, get out arrangement. And you'll recall that DARPA's vision was originally to use soil in the chemistry. So that would work where we have a mission with earth moving equipment as an option. But for a smaller, faster mission, you need to take everything in that you need. Soil is about 6% efficient by weight, which meant that 94% of that weight was unusable. And then the best solid scrubbers on the market, only about 12% efficient, so 88% would be dead weight. So aqueous scrubbers also heavy, low efficiency, voluminous as far as the quantity of fluids that you have to operate it. And then we got down to ammonia, and I'll have to give another guy that I didn't even think about until just now, Dr. Michael McNaughton here at Southwest Research Institute, credit for coming up with that idea. It was a very novel approach, but it gives us a theoretical possibility of nearly 100% of availability, but just based on collision theory. You have one molecule of ammonia available, and it will interact and grab a single molecule of acid gas. So it's not limited by surface effects that the solids are, and so forth. So then the next question is, how do you carry it? And there were several options. I guess I won't go through all of those, but the best one that we came up with was a concentrated aqueous ammonium hydroxide. It flows, it can be pumped, it's low pressure. Water provides some useful cooling, and it's industry standard and mature. So going through all the options, we wound up with going forward with aqueous ammonium hydroxide as the and concentrated aqueous ammonium hydroxide as the acid gas scrubber for the system. We then had to, it's a great idea, let's test it. So proof of concept was we have, at least in this little image, we did a test where we flowed ammonia and we mixed it in the gas phase with HCl in a test chamber. So I've just got 1 second interval images here. And you can see the solid ammonium chloride dropping out. So it's two gases flowing together and a solid powder falling out. And we had the same observation with SO2. We had to add a little bit of water to the gas phase, but exactly we added in exactly the same amount that is expected in vehicle emission, and it worked out great. Dropped out a solid white powder as well. Also, we measured particulate size so we could design a way to capture the solid powder. What do we need to either filter it or separate it from the gas stream? Going into a little bit more detail on the ammonia, and so this is a trace, probably a little more detail than I need to get into today, but so we've got HCl flowing. This is that same test, and this is a FTIR, a Fourier transform infrared spectrometer. And it can look for HCl, it can look for ammonia. So we have it watching for the HCl, we have it watching for ammonia, we've got HCl flowing on the top. And then as we flow the ammonia, and you can see the blue line just starting to go up. As soon as the blue line goes up, the red line, which is the HCl, goes down. And then it goes down to non-detect. So what we did was we flowed ammonia in slight excess to the HCl. So if HCl wasn't there, it would look just like the HCl line in reverse. It would have a high peak. But because it's dropping itself out, the ammonia is dropping out with the HCl. All you're seeing in this slide is the excess ammonia. So when we flowed ammonia, it took it out. It took the HCl out pretty much quantitatively. And then again, we have the same type of traces for SO2, and then HCl and SO2 would be the ones that we'd be interested in. For example, mustard. So here's a very simple and very early process flow of what we had in mind. And you'll see generation 2 and generation 1. So generation 2 was what would be focused on later. Once we solved the problem at hand, then we would look for a transition partner and go for a generation 2 system that would incorporate possibly munitions access and straining the agent material and possibly rinsing the round. So there were some things that we knew that were coming up in generation 2. But we focused more on the fundamental science of the system, and then making it at least a workable prototype. So we'd start up a diesel engine on diesel. We would switch to chemical warfare agent when it was warmed, and it would produce power. So think about power, though. If you just idle your car, it uses very little fuel. And if you rev your engine while it's parked in the parking lot, it spins faster, but the fuel, it sips fuel. It's still just using a little bit of fuel, and it doesn't guzzle fuel. But if you're going to tow a heavy trailer up a steep hill, you are guzzling fuel, and that's what we want this engine to do. We want it to guzzle chemical warfare agent. So we want to be able to go through a mission and make it just think it's climbing Mount Everest. So we had to figure out a way to sink the power, and what's also universally available besides soil is air. So we just made it into a big air pump. So we made as much air as we needed, not as much as we needed, we made more than we needed. We supercharged the engine, so that was fun. And then we used some of the air to do other things on the system, and then we wound up just dumping the rest of it. So we had quite a bit more air than we needed. Then the exhaust would go through a way to knock out the polyphosphoric acid. I'll cover that just a little bit more in another slide. And then we'd send it through the exhaust would then go through a reaction chamber where ammonia was introduced, and we're able to drop out the acid gases. And then after that, once we knew what the particulate size was that we were producing, cyclone separators would do the trick of knocking out about 98% of the particulates, at least of the size that we were making. So we'd be able to knock out nearly all, 98% anyway, of the the particulate matter that would be produced in the process. So we did so we got the bigger engine, we got the 4.5 liter, and we did some fairly simple modifications to it. All of these are normal within the racing industry. They sound pretty exotic, but literally we were sending parts out to racing shops and getting them back in a very short time. So we had Inconel valves made. Nickeloy was an alloy, high nickel alloy for the seats. We added gapless piston rings, and those were installed here at Southwest Research Institute. We added pressure transducers. That's what the graph in the upper right is. You'll see the purple line at the bottom showing the benefit of a modern electronic fuel injection. So you think about how fast an engine rotates, and we're able to inject 2 injections during a single compression cycle. And we would inject a little bit of fuel at this minus 20 degrees top dead center, before top dead center, and start the combustion process as combustion went up. And you can see the combustion takes off vertically at about minus 10. And that's when you got a fireball. We got a fireball in the piston. And then on top of that fireball, then we inject the rest of the fuel. We make the second injection for the destruction. So we're able to time the injections to maximize consumption and maximize combustion in the engine. So the pressure is also noteworthy. The goes up to about 100 bar just for reference is 1450 psi. So that'll give you guys a reference for how much pressure is in there, about 1450 psi. We ran 2 superchargers. Here it is with we call it the doghouse configuration. We have this peaked inlet plenum, and we flattened it out later on once we figured out we didn't need a separating baffle that doghouse accommodated. And then we demonstrated excellent results. We had 5 nines, 99.999% destruction and removal efficiency. And we figured out how much air we were producing, which gave us a good engineering number that we could work to as to how much air we had available to do the other things we needed air to do, which included shearing or aspirating the ammonia and the ammonium hydroxide into pure ammonia in a gas phase. So then for the get in, get out, we needed it put into a vehicle, which we already, of course, some of these things are going on parallel. So we were doing this design at the same time we're doing the test. We named this thing the Expeditionary Destruction System, EXDS. That's what we designed. We did a 3D mock-up of everything that would go into the vehicle. A quick top-down look again for the system. We had, I guess what's interesting on this one, the block flow diagram at the top, it shows the use of the air. So you have the supercharger, the air going to the engine, the air goes to the reactor, the air goes to the cyclones, and then it vents. So the air going to the cyclones was, it is dilution air, but it had a purpose. The different ammonium salts, ammonium fluoride being the one that had the lowest sublimation temperature, we had to drop the temperature all the way down to 120 C or lower in order to drop out the ammonium fluoride when we got to a fluorinated compound. So in order to do that, we had to use some of the air to continue to drop from the supercharger to continue to drop the temperature of the gas and get it to drop out the ammonium fluoride as a salt. Ammonium chloride drops out at 350 C, so that one would come out just almost immediately. So in the top-down picture of the truck, we've got the modified 2 superchargers, modified engine with 2 superchargers. Then the air goes through, the exhaust goes through a heat exchanger, then goes through what I've got marked here as a condensate filter. That's our polyphosphoric acid knockout. So it's a cyclone separator, and the heat exchanger gets down below about 300 C, actually comes out of there about 250. At about 250, at about 300 C to 250 in that range, the P2O5 in the exhaust, it's a solid particulate, interacts with the water in the exhaust and makes phosphoric acid, and those interact and make polyphosphoric acid. That happens really fast, certainly fast enough that we can drop it out by the time it gets a little bit further down the pipe in this cyclone separator, and we would drop out polyphosphoric acid in this area so it wouldn't go into the ammonia reactor. So that would be a waste stream of its own. And then we have the ammonia reactor where we introduce ammonia into the exhaust, and they mix, and the ammonia and the acid gases combine to make the ammonium salts. And that comes out of the top of the reactor and then goes into 2 cyclone separators, which knock out, like I said, about 98% of the salts. So the system design also would have a stack. In this particular one, we don't have it drawn here, but out in the fielded unit would have a small stack that would be erected. Okay. So it's good to have a design. This is what we built, and it's always good when what you build looks like the design. So the only reason I added this or included this slide was to introduce also the air. So you see on the topmost pipe, and then down the upper left side and across the middle, and intersecting at the what we're calling the cooling air union. That's the supercharger air going back to the just before the cyclones, and then that really only amounted to a part of the air. We dumped a lot more air right out of the supercharger than we did using it on the back. So we were pumping a lot of air. Let me go to the next one. So here it is all together. In the lower center photo is the engine with the final two superchargers, the doghouse, the inlet plenum, now a flat top instead of the peaked ceiling there. With the concept of drive in, drive out, we put it in the vehicle. That's what we built. It was capable of driving. When we tested it, we took out the drive shaft because we didn't want to have any unexpected incidents happen. So it was drive in, drive out all the way up to that point. As you can imagine, though, just look at the truck. It can be scaled in a couple of different ways. One is it can be scaled parallel, where you have multiple of these trucks in order to scale the mission larger. Another approach would be to just use a larger engine on a different platform, so you get a larger engine. And then, also the engine doesn't necessarily have to be in the power source for the vehicle. We have a skid-mounted design. So there'd be other options for getting the engine into the field and using it. It doesn't have to be the one that powers the vehicle. The operation is straightforward. Everybody gets it. As soon as you describe what we're doing, of course they get it as, you put the agent in the gas tank. And you just shake your head, yes. So it's not quite that simple, but yes, we have a tank for agent, and that's what's fed to the engine as fuel. And it's not a mix, at least for our testing, wasn't a mix, and we wouldn't expect it to be a mix for mustard. We didn't expect it to be a mix for GB, but we didn't get to test it. So we would, basically switch from 100% diesel to 100% chemical warfare agent, and the engine would adjust to the new fuel and just keep burning it. The goal, of course, would have been achieved to take this out in the field with minimal logistics and leave little to no residue behind, depending on the size of the stockpile being destroyed. We tested the system both at Southwest Research Institute here in San Antonio and at CDC in Maryland. Here at SwRI, we did 315 liters of Simulant. There we go. Destroyed in small scale tests, and that was April through October in 2019. We consistently achieved greater than 99.99% destruction. We consistently removed greater than 99% of the acid gases. I got to tell you, I was ecstatic the first time I took the lid off the bin and looked into the salt bin and saw this little pile of ammonium chloride salt looking back up at me. That was a good day. The feed rate of Simulant was adjusted to match the power output of mustard. So the Simulants we actually had more energy in them than mustard. So we adjusted everything to normalize it to mustard, so that when we got to test on mustard, we already had the engine matching that power. We built it to carry just one 55-gallon drum, so that became the limiting reagent, and that would accommodate about 100-liter mission. The truck was capable of carrying slightly more than that within its load capability, but space-wise, that made it at least good enough for the prototype demonstration. Then we went to Maryland at CCDC. We operated the vehicle remotely, actually via an Ethernet cable, so we were about 100 yards away from the vehicle. They provided independent verification validation testing for us. The CCDC staff were trained on the vehicle and support systems. The test director for CCDC ran the test, Mr. Raymond DiBerardo, excellent man to work with. And then we had the CCDC Data Analysis Center compiled the data into a final report. So that was a third party, even though CCDC, third party independent data compilation, which, that report's available. So the Simulant mix, won't go into the details. So we had a simulant mix to simulate mustard. It would provide the HCl and SO2 as a combustion product. And so we'd be able to monitor the destruction of the simulant itself. And they were monitoring that. And they got, with CCDC's monitors, 99.9988% destruction and 99.9995% destruction. And this was right after the engine, so we didn't take credit for any retention or destruction that would take place in the ammonia scrubber, which ammonia would react with mustard and would also react with one of the simulants. But we just, the most straightforward way to measure it was right after the engine. And then we did a good demonstration. HCl was removed to non-detect, essentially quantitatively. And then SO2 was removed to 99.94%. We did not graduate to testing the system with authentic chemical warfare agent. Materials of construction issues brought the testing to a halt in mid-February. We built it knowing that 316 stainless steel would pit, but at a known rate. And we, even with the thin metal, that we needed to meet the load weights, we calculated the pitting would occur slower than our testing schedule. And as schedules do, it dragged out, and the corrosion got the upper hand on us. If I had endured the Hastelloy long lead times, I'd either be telling you about the testing results from chemical warfare agent testing today, or telling you that we stopped because the COVID pandemic intervened. But anyway, the takeaway lesson on that is use Hastelloy. So after the test, we disassembled the engine to observe wear and corrosion effects. The biggest engine-related failure observed was corrosion of the fuel injectors. This one you see here that's marked damage, that's the worst one. You're looking at what's called a pentle. Sounds like pencil, but without part of the letter. Pentle. That's the worst one we had. That's not, we had 3 others out of the 8 that were damaged. The corrosion is from the outside in. As you can imagine, this would affect the atomization of the fuel going in, the simulant in this case. But even with that, we still achieved those, the 99.9988 and the 99.9995% destruction removal efficiency. So the engine was significantly more robust, and had we not had this failure, we probably could have got a few more, at least another 9 out of the thing. This is a fairly straightforward problem to solve for future systems. A durable acid-resistant coating like tantalum or diamond-like coatings would prevent it. And then, of course, here at SwRI, that's one of the things we have a department that specializes in. So for us, this one's not that big a deal, easily solved. The evaluation of things like valves, the valves of Inconel, the seats of Nicolloy, the rings, the gapless piston rings, which were 316 stainless steel, they all survived well. So there's not really anything to report on that. Everything hung together, at least for the amount of testing that was performed. Everything was still sealing and not damaged to the point of failure, and would have made it through subsequent testing with chemical warfare agent. The thing that took us out of going forward with testing is the failure of the 316 stainless steel on the scrubber system. So here's a magnified image of one of the failure holes. This one is in our reactor wall itself. We also had a couple in the heat exchanger at the tight bends in some of the elbows on the heat exchanger. It's typical of acid metal corrosion. We had it evaluated. We've got a materials science group here at the Institute. They took some time and reviewed it. Anyway, it would have been avoided with Hastelloy, a high nickel containing alloy. And again, the future systems would need to be built with a system that, or the metal alloy that resists acid gases significantly. So where do we go from here? So with what we learned in the DARPA program, we're pretty close to having a fieldable or a system. All the bugs worked out of a fieldable system anyway. In a generation 2, clearly we would need to switch to Hastelloy. We would have to add coatings to the injectors. We have to add munitions access. There is a commercial off-the-shelf system that does this. We're also investigating a technology here of our own, but we need to address the things that were listed on that slide that said generation 2. And we need to automate the engine control so that it's more of a push button and self-controlling system, which is fairly straightforward. We didn't have a lot of engineer interaction with the vehicle while it was running. And then of course, to be blunt, I need a contract vehicle, an end user in a contract vehicle to go forward. So the end user would set mission parameters. We'd work with that to help the end user set specifications and build to that specifications, whether that's a drive-in, drive out, or a cargo configuration. And then the scrubber could be also modular, integrated, or eliminated. Actually, one of the options would be just have a stack. So there's various ways to work this thing and go forward with a generation 2. And so I've included my information here, my contact information, as well as that. As for my DARPA PM, Dr. Ann Fisher, to whom I'm again grateful for her support. And then also she could talk to you government to government, so that would be an advantage of reaching out to her. Also, Mr. Raymond DiBerardo with CCDC was my point of contact. Also grateful for his support and insights. And he's another one that can be spoken with if you need government to government communication. So that's all I have prepared for you today. And I thank you for your time and attention. And with that, I'm open to audience questions.
Daryl, super. Thanks so much for that brief, and thanks for your time. And you did get a bunch of questions, and we'll do our best to work through these. So Craig A. Myler asked about your destruction or removal efficiency calculation. Specifically, he was curious if you could describe that and specifically answer whether dilution was part of the removal. And then he went on to ask why you're using DRE instead of measuring whether or not there are hazardous residuals.
So yes, so we did not use dilutions. That was another reason for taking the result right out of the engine output. So we measured our DRE without any dilution. So that is what's coming out of the engine in just the natural engine exhaust. And then run me through what the other questions were again.
Yeah, so he asked you to describe it. It sounds like you did. And then he asked why you chose to use DRE instead of measuring the hazardous residuals.
So we did measure the residuals in the ash, in the salts, in any of the solutions. Certainly we measured, things, what's in the oil, what's in the coolant. So that is in the final report. Didn't pack it into this particular presentation. And we were looking mostly at DRE for the idea of, is it safe to, for a soldier to work and operate this thing in the field. So we looked at the OPCW, which requires greater than 99.9%. That's only 3 nines. And then the DARPA specifications were at least 4, and with the stretch goal of 6 nines of destruction and removal efficiency.
Excellent. You were foreshadowing, because Mark Diglio, who's been one of our presenters and is a CBRN expert, actually asked about the safety for operators. So excellent. And Craig also went on DRE. The last question he had on DRE is, did you feel like your DRE was limited by your analytical detection limits?
No, in this case, actually, we had to. It's a great question. So as you think about the huge systems in the traditional DMIL systems, 300 horsepower ID fans blowing tremendous amounts of air. Those are very hard to read. The DRE, you have to sample for a long time to get a DRE measurement. With this system, because it's so low volume, you can get a very a DRE with significant more mass on your analytical. So no, it was the opposite problem. We were having to desensitize the monitors to get the DRE measurements.
Okay. So David Gillis asks, assuming if you had removed the restraints of fitting in the truck, what would you have done? What would you do to improve the system, possibly to deal with pitting and corrosion? But I'd also like to know in general, what would you do writ large? So
the simplest answer to meet our timelines for the project constraints, we would have made it out of thicker material. So that was the original plan, but we overloaded the weight limitations of the vehicle. So we were going to use a thicker walled 316 and go forward with that. And that would have worked. It would have gotten us to the end point. We knew the right answer was a high nickel alloy, but we ran into problems with lead times to get those ready and fitted into the remainder of the contract period. Honestly, if I knew, it comes down to what you fight for. If I had known that I was going to fail with the material failure, if I didn't convince myself that I would have an erosion through the system, or that I wouldn't have, that was what I convinced myself of, I would have dug in my heels and fought for the extra schedule to get the Hastelloy. So, what should have happened, we knew that was the right answer. We should have dug in and taken the schedule hit in order to get the successful agent test off.
So thank you for that, Daryl. So Paul Fleischman had a question about the engine. He wanted to know how many total hours there were on the engine, and he wanted to know if you did any maintenance between tests. You got to know if you held the Engine Master AMSOIL Engine Master standards or not.
Yeah, so the total hours, so the 315 liters we did in San Antonio, those were run in about 23-liter increments. And each one of those tests, we'd run the engine for about an hour before, and then probably about probably about an hour after, and then for the actual burn was probably only about 15 minutes. So about 2 hours and 15 minutes at 23 liters. So if I did the math real quick, 315 divided by 23. So that'd be about 14 tests at 2 hours a piece. I'll just multiply it by 2.5. So that's not a lot of hours. I screwed up my calculation. I would love to read it to you. Total time on the truck, probably less than 24 hours of total run on the engine. The engine itself, not a lot of maintenance in between either. We did change the oil, at least up to the point in time of what we were going to do for the chemical warfare agent test, if we got to go that far, was not change the oil. I wanted to watch, and we would sample the oil, and we would watch the accumulation as we did more and more chemical warfare agent tests. But at least on the runs, we would change the oil in between each run, take samples of the oil that we changed. So there wasn't a lot of maintenance. There were a lot of things, as we learned in the early development phase, that broke and had to be fixed. But as we kept hardening things along the way, we figured out what would work for us long term and what wouldn't.
So Jeremy O'Kelly from one of our live streams asked a question about efficiency, and he says that the efficiency you gave was that there's about 5 milligrams of agent were undestroyed per kilogram that you fed into it. Where does the undestroyed agent go? Is it in exhaust? Is it absorbed, et cetera, et cetera?
Yeah, so most of it would go out the exhaust. So whatever's not destroyed would be go through the exhaust system. Now, ammonia has the added advantage or property of destroying several of the chemical warfare agents. We did not get to test, how we were sampling right after the engine, and we were sampling at the exhaust of the scrubber system. Our simulants, by and large, did not undergo destruction by ammonia. So at least for that chemical property, that was unique to the chemical warfare agents, not to our simulants. So we didn't get to test, how much more knockdown we would have going through the scrubber. But we would have a little bit of destruction in there. Some would occur, of course, in the ash, not the ash, keep calling it that, in the salt. Some would drop out there, and then some would be get blow by around the piston rings, and some would wind up in the oil. And we had a plan for dealing with the oil because it's an agnostic engine. We just wind up feeding the oil back through the engine as fuel. So we had a plan for the engine, and with oil that's been contaminated, the ash has sample, has residue in it. But by and large, that if it's 5 milligrams out of the kilogram, and I didn't check that math, the majority of that would be going out.
Okay, so Craig Miner came back with another question, and he asked, we talked about you showed a slide that talked about the removal of agent from the munitions, which I think is, most of us know, most of your listeners know, that's kind of one of the hardest parts of this. How do you get it out? Mm-hmm. Do you have any thoughts on that? Is that part of the system? Is there a long-term goal for that? So forth. So
we were looking at a system, not to plug them, but the Valent Technologies has a system, both a system they call the Monarch and one that they call the Viper. We looked at their systems, and we looked at basically it's a drill and drain operation. We also considered, this same system allows for pumping a fluid into the round in order to flush it back out. So we looked at flushing it with diesel fuel. So you'd have the volume of chemical warfare agent that would go into the agent tank, and then you would flush it with diesel that would also go into the chemical warfare agent tank. And those would be, we burned either one at a time or one right after the other. So there was an idea on how to rinse it. We know that what comes out of rounds isn't what comes out of a laboratory. Laboratory chemical warfare agent is beautifully clear, clean, no particulates. And what comes out of a round is ugly, gross, and black. So we knew that we'd have to have separation technology. So we had some ideas for what that separation technology would incur, and then also filtration in order to get the fuel, get the agent refined to a very clean, particulate-free fuel that can go into the injectors.
So Ivar Terods asks, in your research and your analysis, as you looked at this, so we're all sure that you all spent a lot of time talking about it, just like you did around that table 20 years ago. Did you see other areas for this technology? Are there other places that, other agents that could be scrubbed, other ways that you could scrub particulates out of, say, I don't know, some other process? Do you have any thoughts on that?
So yeah, we did. Of course, we're interested in distributing this technology as broadly as possible. It's amazing how efficient industries are these days. Nobody really has an high energy content waste that they don't know what to do with, and that goes all the way to people that destroy laboratory waste. We even thought about making it available for methamphetamine labs, and picking up oddball chemistries like that, even if we had to dissolve some solid materials. So we had all sorts of ideas. We chased, we've been chasing those down one at a time. There is really this is a solution for a specific problem. Is not a really good solution for a general problem. So we haven't found another one as specific as this, where we have something that is a waste that nobody really wants to use in any different manner than just get rid of it.
So then I'll close with this one because we're just about out of time. I think this is actually a pretty good one when all of us saw the Supercharger sticking up through the hood. Can the vehicle drive and scrub simultaneously? Again, from Ivar.
So we actually, one of our thoughts on this was, if you wanted to make it into like a dune buggy, you go in, load up, and just drive out and burn it on your way home. That would be fantastic until you crashed. So the risk was, tremendously. You added an element of risk that nobody was willing to accept. That I'm going to drive this, while I'm burning chemical warfare agent. So that was actually an early thought. It was a fun one, pretty short-lived. But it could. So the idea was this thing would produce enough power, more power than it needs to run, and it feels like it's under load. So it doesn't care if that load was from the superchargers or from turning the wheels and moving the vehicle. There are the bins and so forth for catching the material. You would have to make that somehow move with the vehicle. So right now, at least the design we had, the vehicle would be stationary. The bins would be put in place. It would do its job. The bins would fill up. The bins would be sealed. And if you're going to haul them out, you have to load the bins back onto the vehicle, or a second vehicle haul the bins out. and then decouple and then drive. So you would have things, either things falling along the side of the road, or you would have to make bins that traveled right along with you.
Well, thanks so much for that, Daryl, and thanks so much for joining us today, and thank you for everyone that took time out of their schedules to dial in. As I mentioned at the beginning of the webinar today, Daryl's slides and the recording of his presentation will be made available for download at the HDIAC website. If you're interested in learning more about the IACs or in getting involved as a subject matter expert, presenter, or just simply expanding your presence in our HD user community, please feel free to reach out directly using the contact information that you're going to see appear on the left-hand side of the screen. In addition to monthly webinars such as this, the HDIAC also offers monthly podcasts, biweekly email digests that contain the latest scientific and technical news, as well as a free technical inquiry service with up to 4 free hours of consulting. We can also perform customer-funded work in any of our technical areas via our pre-competed IDIQ contract vehicle. So again, that contact information will be on the left-hand side of the screen in the chat box. And please be sure to join us on the 29th of October for our next webinar entitled Biostasis. This is going to cover our medical technical focus area, and our guest will be Dr. Tristan McClure-Begley from DARPA, and he will be talking about his experience with DARPA's efforts to extend the time for life-saving medical treatment following traumatic injury. In other words, limiting that golden hour. So again, thank you for your time today. Thank you, Daryl. Like us and follow us on social media. And best regards and stay well.
Thank you.